Hello everybody, I am Mika Seppälä. In this video I discuss the inverse operation to differentiation. That is, I want to find functions whose derivatives are given functions. This is difficult, sometimes impossible, but it has many important applications. This leads to the concept of integration. By an antiderivative of a function, we mean an other function whose derivative is that given function. Here in this picture you see graphs of two functions. One is an antiderivative of the other one. Which one is which? We will discuss this problem shortly. This video is an introduction to the concept of antiderivatives and starts a new area of calculus. The formal definition is the following. A function capital Case f is an antiderivative of a function small case f if capital Case f prime equals small case f. That is, if the derivative of the function capital Case f is the function small case f. Using this definition and the table of derivatives, it is easy to figure out antiderivatives for certain basic functions. For example, for the function x, an antiderivative is 1/2 x squared, but also the function 1/2 x squared plus 1 is an antiderivative because the derivative of 1 is 0. So this comes immediately out of a table of derivatives. And likewise, for the function cosine of x, an antiderivative is sine of x, but then we may also add any constant to sine and we get an antiderivative. So, for example, sine of x and sine of x minus 1 are both antiderivatives of cosine of x. In general, any function has infinitely many antiderivatives because we may add a constant which then may vary, and we get from an antiderivative new antiderivatives by this process. In the title page of this video we had the following picture. It shows the graphs of a function and that of its antiderivative. And our task is to figure out which is which. Now, the derivative of an antiderivative is the function itself. Therefore, if the red curve were to be the antiderivative, then its derivative would be the blue curve. But the red curve is initially increasing, starting from the left. Therefore, the derivative would have to be positive, starting from the left. The blue curve takes negative values when x is less than 0. Therefore, the blue curve cannot be the derivative of the red curve. And we conclude that the blue curve is the antiderivative and the red curve is the function. The following result is a consequence of the mean value theorem for differentiation. We have the following. If small case f is a function defined on an interval, and capital Case f and capital Case g are both antiderivatives of the function small case f, then capital Case f is g plus a constant capital Case c, for some constant c. To prove this, we have to show that capital Case f minus capital Case g is a constant. So since capital Case f prime is f and capital Case g prime is f as well, we conclude that the derivative of the function capital Case f minus capital Case g is f minus f, which is 0. By the mean value theorem, we conclude that the function capital Case f minus capital Case g is a constant. We denote that constant by c. And this means that capital Case f is g plus the constant c. Here it is important that the function small case f is defined on an interval. For example, the function 1 over x is defined for x positive and for x negative. And for that particular function, the same result does not hold. We will discuss that later more in detail. So if the function small case f is defined on a single interval, and capital case F and capital case G are both antiderivatives, then capital case F is capital case G plus some constant. From the table of derivatives, we get immediately our first table of antiderivatives. An antiderivative of x to the power p, when p is different from negative 1, is x to the power p plus 1 divided by p plus 1. If p equals negative 1, p plus 1 is 0, and therefore we cannot divide by that. Therefore this formula applies only when p is different from negative 1. But the function 1 over x corresponding to the value p equals negative 1 has an antiderivative which is log of absolute value of x. This is defined for both x positive and x negative. We will discuss this just in a moment. Antiderivative of sine is negative cosine. Antiderivative of 1 divided by square root of 1 minus x squared is arcsine of x. Antiderivative of cosine is sine. The function a to the power x is defined only if a is positive. If a equals 1, a to the power x is always simply 1. That's a special case. If a is positive and different from 1, then an antiderivative of a to the power x is a to the power x divided by log of a. This comes out immediately from the differentiation formula for the function a to the power x. If a is e, the base of natural logarithm, then we have that an antiderivative of the function e to the power x is e to the power x itself, because then ln of a would be ln of e, which is 1. Antiderivative of 1 over cosine squared is tangent, and antiderivative of 1 divided by 1 plus x squared is arctangent of x. This table one has to remember by heart. More generally, if capital case f is an antiderivative of a function small case f, capital case G, that of small case g, and a and b are numbers, then the function a times capital case f plus b times capital case g is an antiderivative of the function a times f plus b times g. And this is immediate consequence of a formula for differentiation. So derivative of the function a times capital case f plus b times capital case g is first the derivative of a times f plus derivative of b times g. The constants a and b come out of differentiation, so this is a times derivative of capital case f plus b times derivative of capital case g, and that is simply a times f plus b times g. Using this last general property, it is easy to figure out that an antiderivative of the function 2 times sine of x plus pi divided by 1 plus x squared is minus 2 times cosine of x plus pi times arctangent of x. This is an antiderivative, and it follows, since negative cosine is an antiderivative of sine, and arctangent of x is an antiderivative of 1 divided by 1 plus x squared. Since the function 2 times sine of x plus pi divided by 1 plus x squared is defined for all values of x, it is defined on an interval. Therefore, all of its antiderivatives are of this form, this special antiderivative that we figured out plus a constant, that is minus 2 times cosine of x plus pi times arctangent of x plus capital case C, where capital case C is a constant. We have that derivative of log of x, natural logarithm of x, is 1 divided by x. But this is defined only if x is positive. For negative values of x, we may consider log of negative of x. Log of negative of x is a function whose derivative is 1 divided by minus x times derivative of minus x, which is minus 1. So we have that derivative of ln of minus x is 1 divided by minus x times minus 1. The minus signs cancel out. It is just 1 divided by x. We conclude that the function log of absolute value of x is an antiderivative of the function 1 divided by x, simply by verifying that the derivatives of natural logarithm of the absolute value of x for x positive and for x negative yield 1 over x. Now, the function log of x and 1 over x, they are defined only for x positive or x negative. They are undefined for x equals 0. From this it follows that all antiderivatives of the function 1 over x are of the form log of x plus some constant c1 when x is positive, and log of minus x plus some other constant c2 when x is negative. So c1 and c2 are constants. They may be the same, but they do not need to be the same. Any function capital F of this form is an antiderivative of the function 1 over x, and this family of functions contains all antiderivatives of the function 1 over x. Differentiation is completely rule-based. For any function f, we can compute its derivative rather mechanically. And if f is an elementary function, then its derivative is an elementary function of the same type. That is, if x is polynomial, its derivative is a polynomial. If x is a rational function, its derivative is a rational function, and so on. Computing antiderivatives is much more difficult. There are elementary functions which do not have elementary antiderivatives. So there are functions for which we simply cannot compute an antiderivative in a closed form, even though antiderivatives may exist, but we just cannot find a formula for them. But we may always approximate antiderivatives using the concept of slope fields. So we assume that a function f is defined for all x. Then, if capital case F is an antiderivative of the function small case f, then for any constant capital case C, capital case F plus capital case C is also an antiderivative of the function small case f. And now if you consider the graph of capital case F and all the functions of the form capital case F plus C, then one observes that these graphs fill the whole plane. Therefore, we may look at the so-called slope field. An antiderivative of a function small case f is a function capital case F whose derivative is the small case f. So when the function small case f is known, then we know also all the derivatives of the function capital case f. And we may fill the plane with little arrows pointing to the direction given by the function small case f. And these little arrows form the slope field of the function capital case F. Just in a moment, I go through the steps of figuring out the slope field for some given function, and in that process you will see how the slope fields are formed. But using the slope field, it is possible to approximate the graph of an antiderivative of any given function f through any point x0, y0. Consider the task of sketching the slope field defined by the function y equals x squared minus 1. Using that slope field, we then sketch the graph of that antiderivative of the function y equals x squared minus 1, whose graph passes through the point 1, 1.5. We perform the following steps. First, we select the viewing rectangle. The point that we are interested in is the point 1, 1.5. Therefore, we select a viewing rectangle centered around that point. This particular viewing rectangle shown here, the x-coordinates range from -1 to 3, and the y-coordinates range from 0 to 2.5. Then we form a grid covering that viewing rectangle, and on these grid points we perform computations. On the grid points we are going to place arrows, and the slopes of these arrows are determined by the values of this function that we are computing with, that is in this case the function y equals x squared minus 1. So to this end we first form a table of the values of the function x squared minus 1 corresponding to the x-coordinates of the grid points. The x-coordinates of the grid points were -1, minus 0.5, 0, 0.5, 1, 1.5, 2, 2.5, and 3. And the values of the function at these points have been computed, and the values are in this table. Here we have our viewing rectangle with the grid and the point of interest indicated by the blue star. We form the slope field simply by first computing the slopes, that is the values of the function. We computed those already on the previous table. The function was x squared minus 1. Its values, that is the slope of the slope grid arrows that we will eventually draw, is 0 if x equals -1. If x equals -0.5, the slope is -0.75. If x equals 0, then x squared minus 1 is -1. Therefore, the slope is -1. If x equals 0, if x equals 0.5, the slope is -0.75. If x equals 1, the slope is 0. If x equals 1.5, the slope is 1.25, and so on. So next, we draw these arrows on the grid points, and the slope of the arrow is given by the value of the function x squared minus 1. That is by the rightmost column of this table. So when x equals -1, the slope is 0. Therefore, for all grid points lying over x equals -1, we place a horizontal short arrow. For all grid points lying over x equals -0.5, we place an arrow that points down because its slopes are -0.75. If x equals 0, then the slope is even steeper, -1. Therefore, the arrows point down as indicated here in this picture. If x equals 0.5, the slopes are again -0.75. And if x equals 1, the slopes are 0. Therefore, here we have horizontal arrows again. And if x equals 1.5, then the slopes, that is the numbers x squared minus 1, that results to 1.25, and the slopes now point up. And as x increases, the slopes start pointing up more and more steeply. So this is the slope field of this function y equals x squared minus 1. Let us take a little bit closer look at the slope field, and now I delete the grid because we do not need it anymore. So we have the slope field arrows, and to get an approximation of an antiderivative of this function x squared minus 1, we simply connect these arrows and form this green curve. So this green curve is the graph, or rather an approximation of this graph of an antiderivative of the function x squared minus 1 that passes through the point 1, 1.5. So if I now even delete the slope arrows, then we are left with our approximation for the antiderivative of this particular function. For many functions, this kind of a numeric way of approximating antiderivatives may be the only way to compute values of antiderivatives. It is clear that as we take more grid points, as the grid gets denser, the approximations also get better. But these are always only approximations. To summarize, let me recall the first table of antiderivatives presented a moment ago. For the function x to the power p, when p is different from -1, an antiderivative is x to the power p plus 1 divided by p plus 1. For the function 1 over x, an antiderivative is log of absolute value of x. For sine, antiderivative is negative cosine. For cosine, antiderivative is sine. For 1 over cosine squared, antiderivative is tangent. For 1 over square root of 1 minus x squared, antiderivative is arcsine. For a to the power x, when a is positive and different from 1, antiderivative is a to the power x divided by ln of a. If a equals 1, ln of a is 0 and we cannot divide by it. So the function 1 to the power x is a special function because it takes always the value 1, and therefore its antiderivative is simply x. If a equals e, the basis of a natural logarithm, then for the exponential function e to the power x, antiderivative is also e to the power x, a special antiderivative. And for the function 1 over 1 plus x squared, an antiderivative is arctangent of x. These formulas one must remember by heart.